Hello and welcome to online lecture on power electronics. And in today's lecture, we're learning the power MOSFET. So first, what is meant by the MOSFET? So MOSFET is nothing but the metal, M for the metal, O for the oxide, S for the semiconductor, and FET is the field effect transistor. And it is one of the member of power electronics which is used as a switching element. There is other elements in the power electronics to work as a switching applications like the BGT or other elements. But as compared to the BGT, the MOSFET have the more advantage or superior than the BGT. Now, how it is a beneficial or advantages over the BGT? So the first difference is that the BGT is switching speed is not more as compared to the MOSFET. And second disadvantage of the BGT is that when BGT is on, it consumes the much more power. So this is the two big disadvantage of the BGT, and this disadvantage is overcome by the MOSFET. First is that its switching speed is very high as compared to BGT. The switching speed of MOSFET is about 100 kilohertz. So that is the high switching applications we can be use MOSFET. The next one is a lower switching loss. That means when any switch is made from the on to off or off to on, in this process there is some power is lost, but in MOSFET it losses the very little power, and hence it is a very applicable for the high frequency application. Advantage of MOSFET is that it have the very high input impedance in the order of the 10 gigaohm, and this high input impedance permit MOSFET gate to drive directly from the microelectronic circuit. That means it take the very little current from the driving circuit, and that is it avoid the losses of the power. So this is a very good advantage of the MOSFET, that is it have the very high input impedance. Next is the MOSFET is a voltage control device, whereas the BGT is the current control device. Again, because of that voltage control device, we can be drive easily these MOSFETs or MOS devices as compared to the BGT. Next one is that MOSFET have the less chance of thermal runaway as compared to the BGT. We know that the thermal runaway is occur in the BGT. That means when the current is increases in this transistor, so it again create the heat, and because of the creation of the heat, again current is increases, and this cycle is goes on continue, and because of that sometimes device may be the damaged. But MOSFET have the less chance to go for the such type of the thermal runaway, and maybe this thermal runaway is avoided by using the heat sinks. Again, next advantage of MOSFET is that it does not go for the second breakdown, whereas the BGT goes for the second breakdown. Before going for the power MOSFET, we first understand the structure of the low power MOSFET. So this is the structure. The MOSFET have the three terminals. One is a source, second one is gate, and third one is a drain. So first is a substrate. Over the substrate, this is a one P type of the semiconductor, and again there is a 2N plus semiconductor, which nothing but the source and the drain. Again there is a one layer. This layer is nothing but the Si2 layer, that is silicon oxide layer, and over the this oxide layer there is a metal is deposited. This is metal, maybe the aluminum or maybe the copper, or sometimes it is a polysilicon. Polysilicon is doped with the highly doped, and because of the highly doped, this polysilicon can be work as a metal. So this is a simple structure of the MOSFET. And from its name, we can understand the why it is called a MOSFET. So M for the metal. This middle structure is nothing but the oxide, and next one is a semiconductor. So first word MOS, that is a MOS, transistor or MOSFETs. Again, this is a symbol of the N channel enhancer MOSFET. Again, MOSFET have the different type of the types. From that we have taken N channel MOSFET, and here is the P channel MOSFET. Now we starting the how MOSFET is work. So first we applied the voltage in between the gate and the substrate. So substrate is connected for the low voltage, or it may be connected to the ground, and we apply the gate voltage. So from that we observe that there is a positive charges, because this battery provides the positive charges to the metal, and we know that. So this structure can be look as a parallel plate capacitor. So this is a capacitor. So, and in capacitor, so basically capacitor is consist of two metal plate. So this is one plate and this is a second plate, and in between there is a some dielectrics, or maybe the oxide. This is a nothing but the dielectric. So this, and when we apply the positive charges at the one end, so there is the creation of the opposite charges for the second plate. Same way, this work as a one plate. This is the first plate, and this semiconductor is work as a second plate. And this middle layer, this is nothing but the SiO2. This is nothing but the SiO2. So this work as a dielectric. So when we apply the battery, so first the metal plate is get positive charge, and opposite plate of that MOS capacitor is becomes the negative ions. So in that way, there is a creation of the negative charges. So here we have shown this positive and negative. We seen in the previous PPT how the negative charge ions are created. So this creation of the negative charge ion in the P semiconductor is called as an inversion, the thin layer containing the mobile electrons. So these are the mobile electrons, so that they can be travel. It's called as an inversion layer. So when the electron concentration in the new thin layer of electron is the same as the whole concentration in the substrate, that means this is substrate, and how many of the holes present, the equal number of the electrons are created in this P type of the semiconductor, then we can be says the inversion layer is, or we can say that the process, so we can say that the inversion process has started. That is the creation of the inversion layer is started. The gate voltage corresponding to this situation is called as a threshold voltage. That means when the inversion layer is created, at that voltage is called as a threshold voltage. In this PPT, we learning the how the drain current is flow from the source to the drain. In last PPT, we have seen that by applying the VGS voltage, we able to create the inversion layer. But our main aim is that to control the drain current, that is this drain current with the help of this VGS. So we connect the source to the substrate, and we apply one voltage, that is VDS, in between the drain and the source. Now because of VDS, there is a two junctions present in the MOSFET. One is a this P-N at the source, and again next one is a P and N at the drain terminal. VDS is the this negative and this positive, and because of the this positive terminal of battery is connected to the drain, that is N, and this P is connected to the very low or negative voltage. So P is connected to the N, and this N is connected to positive, so it becomes the reverse bias. So this junction it becomes the reverse bias. So this PN junction becomes the reverse bias. So this junction it becomes the reverse bias. And at the source terminal, so this is nothing but a negative, and again this is a negative voltage. So it becomes the forward bias. So because of this forward bias and reverse bias, the current cannot be flow in between the source and the drain. Now, when you connect this drain, now when we connect this gate with the VGS, and the voltage of VGS is at the VTH, so that time, so there is creation of the inversion layer, and because of this inversion layer, the electrons from this VDS are able to flow towards the positive terminal of the battery from this drain source. So that means we can be denoted as the electron or the conventional current, that is from the positive drain current is flowing from the D terminal at the N semiconductor, and this inversion layers and towards the source. So this path is completed with this VDS battery as a function of this VGS voltage. That means this VGS voltage, the gate to source voltage, controlling this drain current. As this voltage increases, that means the inversion there is also increases. The channel of the inversion there is also increases, and the more path is available to flow of the current. That means the ID current is also increases. This ID current is also increases. In short, we can say that the operation of this MOSFET when the VGS is equal to 0, that means this VGS is the 0 voltage, VGS is a 0, and when we apply the VDS voltage, so in that condition there is no creation of the inversion layer, and because of the unavailable of this inversion layer, so the current or charge carrier cannot be flow from the drain towards the source. So that means the current is ID is again become the 0. Though we increase the voltage of the VDS as this voltage, so there is again value of the ID is become 0, because without the VGS voltage, the ID value is the 0, and to flow with this ID, there is a must be VGS voltage that is above the threshold voltage. This is a simple graphical characteristics of the MOSFET when we apply the gate VGS voltage. So this is a VGS voltage 2.53 volt, 3.54 volt, and so on. As the gate voltage, that is VGS voltage, increases, the value of the ID is also increases. Below that voltage, that is VGS below the 2.5 volt, the value of the ID is 0. Why? Because the threshold voltage is less than the VGS voltage. That means the threshold voltage is approximate to the 2 volt, and to flow this drain current, there must be the value of the VGS greater than the 2 volt. As this VGS voltage increases, the ID value is also increases. We're discussing the power MOSFET. Now the name suggests that power MOSFET is it should be able to handle the high voltage and high current, and to fulfill these two requirements, that is to handle the high voltage and high current, so we are required to make some modification in the structure of the MOSFET. So first modification is that we adapt the vertical structure of this MOSFET, and second, because of that adoption of the vertical structure of the MOSFET, it able to handle the large current, because as area is increases, the current capacity of this MOSFET is also increases. And second is that by introducing the drip region, so this drip region is able to handle the more voltage or large voltage. And this structure, how it's constructed. So first layer is the N plus, that is substrate layer. Above that is the N minus, this is nothing but the trip region. That is the its doping concentration is lower than the this plus region. Now next one is the P type of the semiconductor, and next one is the N type. So this is nothing but N type of the semiconductor. Now next one is a oxide layer. This is nothing but silicon oxide. This is the metal contact made for the source, and again this is a metal contact for the gate. So this gate is nothing but the connected with the metal oxide, and this is again the semiconductor. Drain is connected again the substrate with the help of this metal. So this is a simple structure of this MOSFET. Now what happens when we apply some voltages, as we seen in the previous, when we apply the VGS voltage, that is the negative and this positive. So this positive. So because of this apply of this positive here, we get some negative charges in opposite side. So these are the negative charges, and because of this negative charges, we get the inversion layer. So when inversion layer is created, when there is a number of this mobile electrons or mobile charges is equal to the concentration of the holes in the p types, at that time there is a creation of the inversion layer. So there is a creation of the inversion layer of the opposite or the electrons or the minority charge carriers. Now what happens when we apply the VDS voltage? So this is nothing but the drain. So this is the D connected to the drain, and this is nothing but the source. So this is nothing but the VDS voltage applied between the source and the drain. So because of this positive voltage and this negative voltage, so this positive voltage is applied towards this negative, and this negative voltage is applied towards the source to this positive, again this negative. So this junction, is become the reverse bias, because this positive is applied to the N. So this positive applied to the N, and this negative is applied to the positive. So it becomes the reverse bias. So this becomes the reverse bias. And to improve the voltage handling capacity, we added the drip division. That is purpose of this minus N or En minus drip division. Now how it works and how the current is flow from the source to the drain, because we want to flow the current, that is ID current flow from the drain to the source. So it is necessary to flow this current in that way with the help of this gate voltage. When this VGS voltage is equal to 0, that time ID is again become the 0. And when this VGS voltage is above the threshold voltage, that time the current start for the flowing from this terminal. So we assume that this voltage is above the VGS voltage, and because of this VGS voltage, there is creation of the inversion layer. And when we apply this type of the voltage, VDS voltage, so this electrons, so these electrons, suppose these electrons enter into the source terminal from this also and from this also, they enter into source terminal. Again they go for the N type semiconductor. Again there is a path of inversion layer, and again there is a N type semiconductor. That means there is a majority charge carrier of the electron. Again they flow from the. So in that way the electrons enter into source, goes to the N type semiconductor, inversion layer, again for the N type semiconductor, and towards the positive terminal of the battery through the drain terminal. So this is the path of the electron, and conventional current is opposite to that electron. That is we showing this path. So this is the path of the conventional current. So in that way, the current flow from the source to the drain, or we can be sent for the drain to the source with the help of this VGS voltage. And this is the IV characteristics of the MOSFETs. So first characteristic is the transfer characteristics, that is plotted VGS against the ID. So this is nothing but the VGS threshold voltage. If the gate to source voltage below this threshold voltage, that time current ID is become the 0, because there is no creation of the inversion layer. And if the inversion layer is not created, the current cannot be flow. And as the VGS voltage increases, so this voltage increases, the ID current is also increases linearly. And again, this is the output characteristics. That means the VDS versus ID at constant the VGS. And again, we can be look as the VGS is increases, the ID is also increases. And from initially it is increases somewhat and it becomes a constant. So this is nothing but the output characteristics of the MOSFET.